My name is Jeff Krause. I have a PhD in chemistry from Queen's, and I am currently employed at the University of Waterloo. Today I'm just going to go through a couple undergraduate level chemistry topics just for my first session here. So the first of these is just to discuss the density of water. The question is just density of water, but I'm going to follow along similarly to the answer given, which just discusses why it is that the density of water tends to peak at around 4 degrees. So density, just to start off, is an average quantity over a volume. So what we're talking about is an amount of mass divided by some volume, right? So water looks like this, and of course what it wants to do is hydrogen bond to other water molecules and kind of fit into this ice shape that some of us might be familiar with. But at the same time, everything is moving around, so that would be temperature, right? So our density, which would be kind of computed by calculating the amount of mass in some volume, it comes out to be some quantity, but then temperature is making everything move and jumble around according to whatever that is, right? So temperature is related to its average kinetic energy, or how fast it's moving around. And so although the intermolecular forces want to pull it into some crystalline shape, it can't quite get into there, because also there's interactions between oxygen atoms, which are repelling each other, and other hydrogen atoms, which also will be repulsive. So these two are kind of in war between each other. And that you wouldn't be able to predict where the maximum density will lie at 4 degrees. It's more of an observation than anything. But it's interesting. So as the molecules slow down, then they're moving less quickly, and so they're going to kind of bump into each other less and be able to fall into this shape. But they still have to be able to move with enough kinetic energy to actually move. Otherwise, they're going to be frozen into one particular orientation, which is also the reason why water has so many different solid forms, because depending on how jumbled it is and how fast you freeze it, it could solidify into a variety of different ice forms. And so as you decrease the temperature relative to its peak, it's going to move less quickly, be able to get closer together due to these hydrogen bonding type interactions that can pull each other closer together, and the density drops. Whereas, if they pull each other closer together, the density should actually increase. And so as they slow down, it's actually not pulling closer together. It's actually this effect of them not moving fast enough to move around. And so you're stuck with, on average, the density dropping, because they can't they can't jumble around. They kind of got this shape that I've shown here. Whereas as you speed them up, they now can move around and reorient themselves to get into this hydrogen bonding shape to get themselves tighter together. So that's why it peaks at 4 degrees relative to 0. And then as they move faster and faster and faster, they then move further apart again, causing the density to drop again. Yeah. And so that's basically what's all written in here. I've just added in a couple little things. I've also made a small mistake there, but for the most part, I'd say that this solution is correct. And I've really just added in a couple additional points about what density is. Okay. Oh. Okay. So if I move on here to question 2, which just asks about the Lewis structure for xenon XEF2. So a Lewis structure, to start us off, is just you represent an atom, say in this case fluorine, and you put dots around it, so it's sometimes called a Lewis dot structure. You put dots around it for each one of its valence electrons. So here for fluorine, I've added 7. The reason for that is fluorine sitting up here, so you can see that it's, if we follow the periodic table, right, its valence will have 1, 2, 3, 4, 5, 6, 7. Right, so there should be 7 electrons in fluorine's valence. Xenon is where things get tricky. Okay, so as we move down here into this area of the periodic table, we now have xenon's valence is going to be 1, 2, 3, 4, 5. So it'll be 5s2, 5p6. But of course there is a 4d10 in there, right? But for the Lewis structures, we're just going to ignore that. So the way that you would draw that is just with 8 dots around it. Now why I say that things get funny in this block is because as we get up higher and higher in our principal quantum number, which is these numbers here, the energy levels get closer and closer together, and that means that, now this isn't quite correct, but this is kind of the way that we can visualize it. That means that the valence for xenon could be this, but we could also represent it like this. And so that will take a small energy expenditure, but could be made up for in bonding, or could be this. And I believe we could also go up another 2 electrons. So that basically is the reason why for these high principal atoms, you can sometimes get, say, 8 bonds around xenon. Now, the one that we'd be concerned about here is this one, because here we've got a full valence for xenon F2, we need 2 bonding electrons, which mean we just need to promote 2 electrons to give our 2 bonds. And so the Lewis structure for that would be something like this, where now we have, for our fluorine here, we can see we have 1 electron for bonding, and for xenon we now have 2 electrons for bonding, so we can form our 2 bonds. And so if I clean up a bit of space here, we have our fluorine with that, and our xenon in the middle. And clean up a bit more. And again, our fluorine on the side. Now the exact structure you would follow, likely you would have VSEPR rules that you'd be going through. And then to finish our Lewis structure, we basically connect our bonding electrons as a line, like that. And then we see here that that is the solution here that's given, so this solution is correct. And hit that. Okay. And I'll just go out to a blank one here. Okay, so what is this is my 3rd question here. So what is a Balmer series? This solution I think is missing a bit actually, but the different series of hydrogen were given special names by the people who first discovered them, as the hydrogen's atomic spectra were the first to be discovered, because they're also the simplest. So the energy levels of the hydrogen atom are just given by the Rydberg constant over n squared, where n is our principal quantum number. So the same principal quantum number as I was talking about in the previous question. And so the line spectrum comes from transitioning between 2 of these levels. So it's always calculated from a change in energy. And the best way I've always found to represent this as n lower squared minus 1 over n upper squared. The reason I say it like this is because depending on whether you're talking about absorption or emission, the delta could be construed differently, but your energy will come out negative if you use an upper n here. So you always want to use the lower levels n value. And so to actually answer the question here, which is what is the Balmer series, the Balmer series are all the transitions where the lower level is 2. So they'll always have this form. And they always come from an upper level because they're emission lines as opposed to absorption lines. Or at least they're observed in emission. So that means that the n upper here is some integer above 2, so 3, 4, 5, etc. And so if we look here, so the Balmer series is a series of spectral lines present for the hydrogen atom. it's not quite when they transition from n equals 2 to a lower level, as in that case, actually there would only be one option for that, and I believe that's actually in the Lyman series. And yeah, there are 4 visible lines, so that is correct. So I would say the Balmer series are all hydrogen transitions from a higher energy level to the n equals 2 state. Right. But other than that, it's correct. I don't know. It's fine. Okay. Okay. So that's all the questions I'm doing for this first session. If you enjoyed this, please subscribe to OneClass and visit the links. This has been Jeff Krause, and I hope to see you again.